welcome back to the Combo Class Bonus channel. I'm your teacher Demotro, and I thought it was time for another little bonus math lesson to clarify some things about the magical subset of math known as modular arithmetic. Now, of course, one of the reasons I like modular arithmetic is it's so clock-like. Clocks are basically working in what's called mod 12, except that they wrote 12 where it should say 0. But we're going to go a little smaller to half of 12 and look at what mod 6 would contain. And why don't we whip up a mod 6 addition and multiplication table from scratch? And you could use similar methods if you were ever playing around with a different mod. Now, in mod 6, what this means is that we're looking at integers or whole numbers, and we're categorizing them based on their remainder they'd have if we divided by 6, or how much more than a multiple of 6 they are. And so the options for that are going to be 0 more, which are the multiples of 6, which are also known as three-even even numbers in the combo classroom. And then you get your 1s, which are post-three-even rods that are also odd. And then you get your 2s, your pre-three-even evens, which are throd, but of the pre-three-even variety. And then you get your three-even odds, the ones congruent to 3 in mod 6. And we'll be using the term congruent for numbers being equal to these, because congruent, written with 3 lines, kind of like a mega equals sign, is the modular version of saying something is equal to that. And you can also imagine it as if I had only 6 hours on a clock and I started at the top and I spun an amount of some number of hours, what number would I end up on? Now, after 3, we get the ones congruent to 4, and those numbers are our post-three-even throd but even numbers. Then we get our congruent to 5s, which are our pre-three-even throds meaning not three-even, which are also odd. Each of these have a fun nickname we could add to them, and if we just use pre-three-even and post-three-even to distinguish 2 types of throd number, we can call these three-even evens, post-three-even throds, pre-three-even evens, three-even odds, post-three-even evens, pre-three-even odds, and all those are unique titles, all the combos you could imagine. Now, since we have one axis of these, if we want to interact it with some more numbers using an operation like addition or multiplication, we're going to need another axis. So let's get 0, 1, 2, and all the way up through 5 on this side as well. Now, we're only making one table here to start, and you know, maybe I should have made 2 tables for addition and multiplication, but we're mostly focused on multiplication. We'll take a quick peek at the addition and then maybe erase them or draw a second mod table. This, as you know, is just a bonus lesson, and if you want a little more precision, head over to the main combo class channel. We've done a lot of modular arithmetic there, but we got some more fun stuff to make sure you guys understand. Now, if I'm doing addition in this mod, 0 is just going to leave the numbers as themselves. 1 is going to slide them up 1 or almost over 1 because we add 1 to all of these early ones, but by the time we hit 5, adding 1 to that gives me 6, which goes back to 0 in this mod, a multiple of 6. So it sort of slides it over, if anything, going around the bend. Similarly, we would add 2 to each one here, as long as they fit, and then we would cycle back around. 4 plus 2 is 6, which is 0 in this land. 5 plus 2 is 7, which is 1 in this land. And so if we continued the addition table, we would get these diagonal stripes of each number, and we would also get some mildly neat patterns, but nothing as special as the multiplication table. The addition tables are pretty predictable. Each row will have it slid over in a cyclical way from the last, and each number is going to get its own diagonal stripe appearances. So why don't we wipe off these addition ones and pretend that the operation we were using on these two axes was multiplication. Now with both of these operations, since a plus b is the same as b plus a, and since a times b is the same as b times a, we know these will be symmetric charts. They're going to have some diagonal axis that's going to be reflectable on each side of it in a symmetric way, because 1 plus 4 would be the same as 4 plus 1, or 1 times 4 would be the same as 4 times 1. So we know that the multiplication chart won't really matter which axis we say is the first one multiplying to the other, and so it's going to have a certain sort of symmetry. Now, if it has a symmetry around the diagonal axis, we know the diagonal axis might be notable. So let's make sure to remember that these are the cells right along an important line where that reflection is happening around. Now, multiplying in mod 6 now, we can see that 0 times anything is going to clear a whole row of zeros. Wipes out all of this stuff. Now, what about 1 times anything? That's going to give us a row of the numbers themselves, because we're just multiplying them by 1. So we get what looks like our natural numbers before they end in a cyclical way, going down that line and going down that line. And here we can start to see some of that symmetry I was mentioning, where we have those reflected, those reflected, those reflected, and so on. Now going a little further, 2 times 2 will give us 4. But 3 times 2 gives us 6, which in this land is 0. And 4 times 2 gives us 8, which here is 2. 5 times 2 gives us 10, which here is 4. And we could see we got the pattern twice, kind of. It went 0, 2, 4, 0, 2, 4. Now if we go a little lower to see what happens when we multiply them by 4, we can end up deducing the exact reverse for where those 2's and 4's go. The zeros still land at the same spots because 4 times 3 is a multiple of 6, giving us 12, so we get a 0 there. But now instead of going 0, 2, 4, 0, 2, 4, this row ends up going 0, 4, 2, 0, 4, 2. And we could just do those calculations by multiplying any numbers and then seeing what amount is it higher than a multiple of 6, or divide the answer, like in this case 5 times 4 gives us 20, by 6 in a way that we can look at the remainder, which would be 2 there. Now what happens on the 3 row? Well, we got 3 times 0 is 0, 3 times 1 is 3 itself, 3 times 2 is a multiple of 6, so it gives us 0. 3 times 3 ends up being 3 more, and we get 0's and 3's alternating. Now how about this last row? We got 5 times different stuff. 5 times 2 is 10, that's 4 more than a multiple of 6. 5 times 3 is 15, that's 3 more than a multiple of 6. 5 times 4 is 20, that's 2 more than a multiple of 6. And do you see where this pattern's going? We have what looks sort of like that natural number row in reverse. And mod 6 is so elegant and neat because all these patterns have this nice copycat or extra patterned or flipped version of the other patterns, and it feels so self-contained and nice compared to mod 10, which is similar to the base 10 system we count in and how last digits of numbers work. If I made a base or a mod 10 chart like this, it would be telling me traits about what we think last digits of numbers are, because our last digits of numbers are the ones placed in base 10, which basically makes it all mod 10-y. And that's not the ideal mod. 6 and 12 have such better traits than 10. But in any case, we've mentioned a lot about looking at the diagonal here, not just in terms of reflectiveness, but in terms of maybe the diagonal ones have some importance to them. Now, if you remember on my more full times table episode, when we made a massive times table and imagined it being infinite and thought, what patterns would you see on an infinite times table? We can remember that the square numbers land on the diagonal, because that would be the spots where we have 1 times 1, 2 times 2, 3 times 3, or anything times itself. So similarly, the spots where anything times itself happens are on this diagonal. And every number, we said, or every whole number, every positive integer, can be put in one of these 6 classes in Mod 6. So no matter what positive integer we pick, if we want to square it, it's going to represent one of these things on the diagonal. We got 0, we got a couple 1s, we got 1 3 and a couple 4s. And we don't have any 2s, and we don't have any 5s. And what does this tell us? This tells us that no square numbers are 2 or 5 more than a multiple of 6. We could also phrase the 5 one as no square numbers are 1 under a multiple of 6. And if we explore that in different mods, we learn a lot of weird traits about square numbers. So these numbers have an important name. They're called the quadratic residues of Mod 6. And I'm sure we'll return to quadratic residues again soon. They're pretty awesome, have a lot of cool number theory applications. But in general, I just wanted to show you guys how we whip up a little modular table and some of the fun patterns in it. Thanks for joining me on this bonus lesson. We'll have some awesome full lessons coming on the main channel soon and some short videos here. And I'll see you soon.